This video is part 2 of a lecture from section 4.4 from Math 311, a course in linear algebra at Western Illinois University. In the first part, we did some examples and we showed that some certain matrices, we could use the eigenvalues and eigenvectors of certain matrices to put it in a certain form to give it a relation to a diagonal matrix, which made computations a little easier. In particular, we wanted to find an invertible matrix P such that P inverse times A times P was a diagonal matrix. And now we're going to examine the theorem of what we did, why we were able to do what we could do with those examples. So this is the theoretical part. We want to basically talk about two things: similarity and diagonalization. And the latter is actually a specific case of the former. So if A and B are two n by n matrices, we say A is similar to B if P inverse AP is equal to B for some invertible n by n matrix P. Okay. Now this is actually the relation is similar to is actually what we call an equivalence relation. It's going to actually turn out that that A is similar to A, and if A is similar to B, then B is similar to A, which is the first thing we have here. And we also have that if A is similar to B and B is similar to C, then A is similar to C. Okay, those are proofs of that in your book. We're not going to be using that last relation too much. But here's what the relevant parts we have. If two matrices are similar, if A is similar to B, as I just said, B is similar to A. The determinant of A and the determinant of B are the same. They have the same characteristic polynomial, and if that's the case, then they have the same eigenvalues. And then the corresponding powers of A and B are going to be similar to each other. And that's true. You can even bring in negative exponents if A is invertible. And then we're also going to see that if two matrices are similar, they have the same rank and they have the same nullity. Okay. All right. So we're going to actually prove all of these, and the proof of this one isn't going to be too bad. So, well, first of all, if A is similar to B, then P inverse AP is equal to B. And we can multiply on the right by P, and rather on the left by P and on the right by P inverse. Okay, and then these cancel and these cancel, and we just get A is equal to P inverse. Okay. And then this shows that A is similar to B because P inverse is invertible and its inverse is P. So remember the actual matrices here don't have to be the same. They just have to make sure that you have whatever is here is the inverse of the matrix here. So A is invertible. So B is similar to A. All right. So that proves one. To prove two, if the determinant of A equals the determinant of B, well, the determinant of A we now know is A is P inverse. And we know from the properties of determinants that the determinant is multiplicative, so this is going to be the determinant of P times the determinant of B times the determinant of P inverse. And this last determinant we also proved this is equal to 1 over the determinant of P. Okay, so this factor and this factor cancel out, and we just get the determinant of B. Okay. So that proves 2. To prove 3, we want to show they have the same characteristic polynomial. The characteristic polynomial of A, let's start with the determinant of the characteristic polynomial of B. So the characteristic polynomial of B is the determinant of B minus lambda I. But right now we're just going to take lambda as an indeterminate. And remember, B can be written as P inverse AP. And now we can write that this is just a, we can treat this lambda as a variable, but it's also a scalar. It's not a matrix. So really we just have the identity matrix, and we can write this identity matrix as P inverse P as well. Okay, and in fact this will be the determinant of P inverse AP minus P inverse lambda I P. Okay, and then we can notice we can factor out a P inverse on the left. And then factor out a P on the right. So now this becomes the determinant of P inverse, determinant of A minus lambda I times the determinant of P. And once again, these determinants will cancel out. And so this is the determinant of A minus lambda I. Okay. All right. Now, so the characteristic polynomials are the same. So that proves 3. And 4 is true because the characteristic the eigenvalues of B, this is equal to the roots of determinant of B minus lambda I, which is equal to the roots of the determinant of A minus lambda I, which we just proved are equal. And so these are the eigenvalues of A. So that proves 4. Okay. Okay. To prove 5, in 5 we're using the same trick we used before in some of the examples. A to the M. This is going to be so that this is PB, P inverse to the M power. And so this, we can rewrite this as just PB, P inverse, PB, P inverse, multiplied by itself M times. And you'll see that they're going to be, the P inverse and P here cancel out here. All the P's cancel out except this one and this one at the end. So this is going to be P, B to the M, P inverse. Okay. So that proves, so A to the M is similar to B to the M. And in fact, if we want to show it's invertible, to show it's invertible, we have we can just take well, to show that A is invertible, we can just take A. We have A is equal to BP B inverse, and then take the inverse of both sides, and we can see that this will be P inverse inverse B inverse P inverse. So this will be P B inverse P. All right, so we can see that A inverse is similar to B inverse, okay, and the rest follow in the similar way. Incidentally, similar if A is invertible, B has to be invertible, because remember, invertible. If you're an invertible matrix, then 0 cannot be one of your eigenvalues, right? And if A doesn't have 0 as an eigenvalue, B doesn't have 0 as an eigenvalue, so they're both invertible. They're either both invertible or they're both not invertible. All right. For 6, 6, I'll just do this relatively quickly. I don't know if we'll be doing a whole lot with this in the rest of the course, but just to show you, we want to show the rank and the nullity are the same. Well, what we're going to do is we're going to show, we're going to consider the null space of A and the null space of B. And we're going to see that they're different, but there's a bijection or a one-to-one correspondence between these two subspaces. Namely, for example, if we take an element V in the null space of A, so that means AV is equal to 0, and then we can do the following. We're going to show that P inverse V is going to be in the null space of V, right? Because we said that A is going to be, A is the same as P inverse V equals 0, so this equals 0. And then we can apply P inverse to both sides. Okay, and it's not very hard to see that this will be 0 as well. Okay, but this now is P inverse V. So you see that P inverse V, whatever that vector is going to be in the null space of B. Okay. And then similarly, if you take a vector W in the null space of B, you can similarly prove that P times W will be in the null space of A. All right. So these are not what we have. So what we have here is a bijection. A bijection, that's a function from one set to another, which is 1 to 1 and on to, if you remember that. And it's actually a bijection of subspaces. And so there are going to, when you have a bijection of subspaces, they have to have the same dimension. So the dimensions of this is equal to the dimension of, so the nullity of A is equal to the nullity of B. And then we can subtract the rank is just going to be n. If we have n, if it's an n by n matrix, then n minus the nullity of A is equal to n minus the nullity of B, and that tells us the rank of A is equal to the rank of B. Okay. All right. I think there might be some another proof for this, but I think this is kind of cool. All right. So that's about all we have about similar matrices right now. And so we say that if we're interested in the case when a matrix is similar to a diagonal matrix, okay, and if that's the case, then we call it diagonalizable. So we say an n by n matrix A is diagonalizable if P inverse PAP is equal to D for some invertible matrix P and some diagonal matrix D. Okay. All right. Now there's a very straightforward characterization of diagonalizable matrices. Matrix A is diagonalizable. If it's n by n, it's diagonalizable if and only if A has n linearly independent eigenvectors. Okay, so we want to prove why that's true. Okay, first of all right. So why is this true? Okay, so if A is diagonalizable, so P, that means P inverse A P is equal to D. And well, let's say that D is some diagonal matrix. We select lambda 1 through lambda n with zeros everywhere else. And let's let P, let's have the columns of P be denoted V1, V1, V2, and so on to Vn. So these are the column vectors that make up P. And because P is invertible, that means that these vectors V are linearly independent. And that follows from the fundamental theorem of invertible matrices. All right. So now, if we have this, we can from here we can multiply both sides by P, and so we get AP is equal to PD. And then, so this means that A times the vector, the matrix V1 through Vn is equal to V1 through Vn times this matrix lambda 1 through lambda n. And then what this becomes is, as we mentioned before, this is AV1, is the column of the new, first column of the new product, and so on, and this is, the last column is AVN. And we said that when we multiply this is lambda V1, that's lambda Vn. Okay, and so we get that AVI is equal to lambda I VI for all I. Okay, and we know that, and we also know that VI is not zero. None of these columns can be zero, because if they were zero, then P couldn't be invertible. So that means that so V1 through VI, Vn are linearly independent eigenvectors. Okay, so that proves one direction, and proving the other direction is almost basically the same as in reverse. Okay, if we start out by having n linearly independent eigenvectors like this, then we have, let's say, A VI equals lambda VI for all I, and then this implies this, and this implies this, and this implies this. And where we define P, we can define, where we're defining P to be this matrix. We know this matrix is invertible because the columns are linearly independent, so P inverse exists, so we can multiply that, and we get this. So we get it's A. So A is diagonalizable. So we're basically, we can just reverse the direction, and that proves the other direction. All right. As a nice corollary of this is that if an n by n matrix A has n distinct eigenvalues, then the A is automatically diagonalizable, because we know that we proved last time in the last section, I think, that if we have that if eigenvectors have n distinct eigenvalues, then they have to be linearly independent. Okay, we proved that in the last section. So that's why it's always diagonalizable. However, there are lots of cases where where you can have repeated eigenvalues, or you can have many vectors with the same eigenvalue, many eigenvectors with the same eigenvalue, and still be diagonalizable. However, there are other cases where they're not diagonalizable. And our next goal is to find what is the necessary and sufficient criterion for a matrix to be diagonalizable. And it all comes back to the two kinds of multiplicity of the eigenvalues. It's not so much the eigenvectors, it's the eigenvalues. And in particular, it's the geometric multiplicity and the algebraic multiplicity of an eigenvalue. We have this result that says that the geometric multiplicity of lambda is an eigenvalue, the geometric multiplicity of lambda is always less than or equal to the algebraic multiplicity of lambda. Now, before we go on any further, let me just remind you that geometric multiplicity this is the dimension of the eigenspace E lambda. So these are all the, instead of all the eigenvectors corresponding to lambda along with 0, that's the geometric multiplicity. And this is the algebraic multiplicity is the number of factors of x minus lambda in the characteristic polynomial of A. All right. Now, Theorem 3 says that the geometric multiplicity is always less than or equal to the algebraic multiplicity of lambda. We are going to prove this, but we're going to prove this a little later. Okay, I want to use this to, we're going to we'll prove that later, and we want to prove the grand finale of this section, which is the diagonalization theorem, which says that if A is an n by n matrix whose distinct eigenvalues are lambda 1 through lambda k, the following are equivalent. First says A is diagonalizable. 2 says the union of the bases of the eigenspaces of A contains n vectors. And number 3 says the algebraic multiplicity of lambda I is equal to the geometric multiplicity of lambda I for all I. Okay. So, a couple things before we go on. We are not saying that the eigenvalues are all. We're not saying that A must have a different eigenvalue for each eigenvector. What we're saying is that if you were to list all the eigenvalues of A without repetition, they'd be in this list. Okay, that's why we have k eigenvalues, not n. All right. So there are no repetitions. So that basically, if you're an eigenvalue, you're somewhere on this list exactly once. Now the main thing we're going to show is that the main thing we want to show, these multiplicities are going to ultimately determine if A is diagonalizable. All right. So I'm not going to give a real rigorous proof. I'm going to give a special case, and then hopefully you can get the idea. One thing we're going to put a little caveat. We're going to assume that all the lambdas are real. So there are no complex. There are no non-real eigenvalues and no non-real roots of the characteristic polynomial. We can broaden things, and we can allow complex eigenvalues and eigenvectors, but then we have to bring in matrices with complex entries, and it's not hard to general all the work we've already done. It's not hard to generalize them to complex matrices, but we're just going to stay away from them. We're not really going to see many. You have many experience with complex numbers in this course, so we're going to assume that everything is real, and then that what that means is the sum of all the algebraic multiplicities of the lambda I. So I going from 1 to k is equal to n. Is exactly equal to, because the n is going to be the degree of a characteristic polynomial always, and if all the roots are, if you add up all the multiplicities of the roots, you'll get n to the degree. All right, so that's what we're going to assume. Now we're ready to go and prove this stuff. All right. So let's start. Let's suppose A is an n by n matrix with distinct eigenvalues lambda 1, lambda 2, and lambda 3. So we're going to just assume that there are three possible eigenvalues. Okay. So we're going to get three corresponding eigenspaces. So let's assume that E lambda 1 has a basis denoted by V1 through VR. Or let's make this U. That's what it was in my notes. And then E lambda 2 has a basis V1 through Vs, and E lambda 3 has a basis W1 through Wt. Okay. All right, every subspace has a basis, so we're good here. And this says that R is the geometric multiplicity of lambda 1. S is going to be the geometric multiplicity of lambda 2. And T is going to be the geometric multiplicity of lambda 3. Okay? Okay, now first we're going to do a claim that says if we take all these vectors and combine them into one big set, that's going to be linearly independent. So we're going to let beta be set of all the U's together, U1 through UR, V1 through VS, and W1 through WT, and we're going to claim that this is linearly independent. Okay. All right. Now, why is that? Why is that, you ask? Okay. Well, if we take a linear combination of these, say C1 U1 plus CR UR plus D1 V1 plus DS VS plus E1 W1 plus ET WT. If this is equal to 0, what are we looking at? We're going to prove we want to show all these scalars are 0. Well, if we take this part and we call this particular sum x, if we call this sum y, and we call this sum z, we get x plus y plus z is equal to 0. Okay, but x is going to be an eigenvector because it's a linear combination of eigenvectors of lambda 1, so x is going to be an eigenvector for lambda 1. Similarly, y is going to be an eigenvector for lambda 2, and z is going to be an eigenvector for lambda 3. Lambda 1, lambda 2, and lambda 3 are distinct, so that means x, y, and z are linearly independent. Since lambda 1, lambda 2, lambda 3 are distinct. Okay. Well, if they're linearly independent, the only way that this sum can hold is if all of them are 0. So that means that x equals 0, y equals 0, and z equals 0. Okay, but that means that this linear combination is 0, and because the u's are all linearly independent, that means the c's are all 0. Similarly, the v's are all linearly independent, so that means the d's are 0, and similarly the e's are also going to be 0 because the w's are linearly independent. So that means that the ci, di, and ei are 0 for all I. So the set B is linearly independent. Okay, so that's kind of a big deal. All right. So now we're going to go and prove this stuff. Okay, prove this. What way we're going to prove is we're going to show that 1 implies 2, 2 implies 3, and then 3 implies 1. So if 1 holds, that means A is diagonalizable. So by theorem 2, A has n linearly independent eigenvectors. Okay, that's from theorem 2. Okay, now let's say, so we have n now. Some of them are going to be eigenvectors of lambda 1, some lambda 2, some lambda 3. So let's assume that, let's say, n1 of which are in E lambda 1, n sub 2 of which are in E lambda 2, and n sub 3 of which are in E lambda 3. Okay, where n1 and n2 and n3, they're just numbers, okay, but they have to add up to n, right? So n is equal to n1 plus n2 plus n3. All right, but at the same time, we know that n1, these vectors, these are literally independent vectors in this space, and the dimension of this space is R. Okay, because so you can't, so n1 has to be less than or equal to R. You can't have more linearly independent vectors than the dimension of your subspace. Okay, which I think we proved, or it's not too hard to, if you think about, because of the uniqueness of dimension. Okay, similarly, if we are having n2 linearly independent vectors that sit inside of lambda 2, so n2 is less than or equal to s, the dimension of this eigenspace, and n3 is less than or equal to t. Okay, so then we get, then this implies that this is less than or equal to r plus s plus t. Okay, which, but R and S and T are the geometric multiplicities of the eigenvalues. So that means this is less than or equal to the sum of the algebraic multiplicities of lambda I, as I goes from 1 to 3. Okay, but this is a sum of all the algebraic multiplicities of all the eigenvalues, so this is equal to n. Okay. All right. So so everything here is equal to each other. So in particular, beta has beta consists as n vectors, n linearly independent eigenvectors. Okay. Okay. But actually, what we really wanted to show is that proves two. That's the union of all the bases. That's beta in this case. Contains n vectors. All right. So this proves 2, which is 2. Okay. So 1 implies 2. To show that 2 implies 3. So now we're assuming that beta has the size of beta is n. Basically, what 2 says. So that implies that n is equal to r plus s plus t. Okay. Well, once again, this is going to be less than or equal to the sum of all the algebraic multiplicities of lambda I. I'm sorry, not n, it's 3 in this case. And this is equal to n. So once again, we have equality here. And if you think, well, r is less than or equal to this number, the first sum here, s is less than or equal to the second number, and t is less than or equal to the third number, but this sum equals this. The only way that this can happen is if everything is equal. So that means that R, because the R is the geometric multiplicity of lambda I equals the algebraic multiplicity of lambda I for all I. Okay, and that proves 3. Okay. Then finally, to show that 3 implies 1, it's not terribly hard either. If 3 holds, then n, which we already know is the algebraic multiplicity of sum of all the algebraic multiplicities of lambda I, as I goes from 1 to 3. This is equal to the sum from I equals 1 to 3 of the geometric multiplicity of lambda I. Okay, but this is just R plus S plus T. Okay, and then, so that means that beta has n linearly independent eigenvectors of A. Okay, that is this set. So A is diagonalizable. Okay, which is 1. Okay, so that is the idea. Hold this test. Will you need to reproduce this test? This proof on a test? No, but it's important that you actually understand what's going on. Where this is such an important result, and we're not just making this up. Okay, this actually follows very nicely. So this was when you had three eigenvalues, and I think you can see it's not hard to do this if you had 4 or 5 or 6. Okay, it would just be a lot more to write down. Okay, so this is just this generalizes very nice. Okay, so in the next lecture we're going to prove that we're going to finally prove why is the geometric multiplicity less than or equal to the algebraic multiplicity. That will be on a separate video, which you can, if you want to skip that, that's fine. But I want to put it out there to show why that works. So until next time, see ya.